This is Miller's planet. It's the closest one to the fictional black hole Gargantua. There's one scene that we're going to focus on today. Have a little watch. So what's so special about this scene? Just in the span of this 5-second clip from this planet, a lot has happened on Earth. I mean, a lot. You might be wondering why. Well, just after the touchdown on the planet, Joseph Cooper said something very important.
7 years per hour here.
So, 7 years per hour. What he means by that is that if they spend 1 hour on that planet, time will pass 7 years back on Earth. So how is that possible? The short answer is that it's because they land here, deep in the gravitational well of an immense black hole. So what is the difference between being in a super strong gravity zone and being in a weaker one, like Earth? To address this concept, we need to visualize it with a simple thought experiment. We have person A floating near a massive object with a lot of gravity, and person B just casually floating in an empty void of space. Person A shines a green laser beam towards person B. Because light is a form of vibration, the laser beam has a color that corresponds to 600 trillion vibrations each second. Now, light is also a form of energy, and as that beam of light comes out of the gravity of the massive object, it loses a lot of energy. This loss means there's a decrease in frequency. So by the time that beam of light reaches person B, its frequency will have decreased by some factor. That means instead of the green light at 600 trillion vibrations a second, person B gets only, let's say, 10 billion vibrations per second, which is a microwave radio beam. This phenomenon is called gravitational redshift. But not so fast. Individual wiggles don't just go anywhere and disappear. Since person A creates 600 trillion wiggles every second, while person B only gets 10 billion every second, the only way this can happen is if 1 second on one astronaut's clock is not the same as 1 second on the other astronaut's. In other words, it only takes 1 second for person A to create those 600 trillion wiggles, but it will take 60,000 seconds, or nearly a day, for person B to receive them. So this is what happens. The mechanisms we use to track time or clock don't all operate at the same rate. And when I refer to clocks, I'm not solely talking about the mechanical device on your wall or your wristwatch. I'm also including the natural processes inside you, the consistent beat of your heart, the rhythm of your breath, even the activity in your brain. Person A takes a breath and takes another breath and measures a few seconds between the two. For him, everything feels normal. Clocks tick the way they're supposed to. On the other hand, person B watching person A through a telescope sees everything in slow motion, with several days passing between the two breaths. I guess it's time to make this clear. Time isn't merely a construct designed by humanity. It arises as the consequence of the physical world of our universe, and the passage is experienced differently by different entities within it. Even Einstein pointed out that the concept of time dilation defies everyday logic.
A somewhat unfamiliar conception for the average mind.
According to Einstein's special theory of relativity, the greater the acceleration of an object, the slower it will move through time. On Earth, gravity's pull is modest. On the surface of a neutron star, where time is slowed by a few hours per day, gravity's pull is enormous. And at the surface of a black hole, time is slowed to a halt, where the gravity is so humongous that nothing can escape, not even light. The concept of this slowing of time plays a major role in Interstellar. Miller's planet is depicted as being present in warped space-time near the black hole Gargantua. Because of this, the planet exists deep within the black hole's gravitational well. So, although it's in a stable orbit and in free fall, which means the astronauts don't feel the black hole's gravity, they're still under its influence. So if we apply Einstein's relativity here, we would know that Miller's planet would experience time at a very slow rate. But here on Earth, gravity is at a modest rate, and the gravitational force of the Sun is also 1 billion times weaker than Gargantua. So while the 3 astronauts spend a few hours on the planet, decades pass in the outside universe. All of this information is brought to you from the book The Science of Interstellar, written by the scientific consultant for the film. In real life, this process is happening everywhere in space. One interesting example is our International Space Station. When the ISS moves fast in orbit, time dilates or slows down, compared to a stationary observer here on Earth. Technically speaking, it is in a different time frame than we are. So by calculating the difference between Einstein's equations, we could correct the time at the ISS.
Because we use a lot of references to the movie Interstellar here, we might as well just take a case study of how filmmakers technically do this time dilation feel in the movie. In the opening scene, when Cooper and his team step on Miller's planet, an intense music with clock-ticking elements starts. For every 60 seconds of the track, there are 48 ticks of the second-hand sound. So, each tick is an interval of 1.25 seconds.
According to the movie, every hour on Miller's planet equals about 7 years on Earth. Let's do the math on this.
There are 3,600 seconds in an hour, and there are 24 hours in a day. So, to get 7 years, we need to multiply. Seconds in a day, days in a year, all multiplied by 7 years. Roughly, we'll get about 221 million seconds in 7 years. This gives us a conversion factor of about 61,400 seconds, which pass on Earth for every second spent on Miller's planet. Multiply this by the interval between each tick, and you get 77,000 Earth seconds, or about 21 hours.
And this is a side-by-side comparison of what happens on Miller's planet versus Earth in real time. After grasping all of this information, of course we want to ask the following questions. Is this extreme time dilation plausible in real life? Could we even land on the surface of such a planet?
To achieve this extreme time dilation, where 1 hour over there equals 7 years on Earth, a planet would need to be incredibly close to a supermassive black hole, nearly at its event horizon.
At this distance, the gravitational forces would be so strong that they'd likely tear apart any ordinary object. Maybe the planet would need to be made of some exotic form of ultra-dense matter to avoid being torn apart. Even if such a planet existed, visiting it would present another challenge. Escaping the deep gravity well would require enormous amounts of energy, far beyond our current technological capabilities.
But anyhow, if they wanted to get all the science correct, we wouldn't be able to enjoy the movie. After all, it's science fiction. And to make a great film, a superb filmmaker often pushes things to the extreme. But in our case, it's sufficient enough to turn the concept of time dilation into a beautiful film.
We'll find a way, Professor, we always have.
I want to briefly revisit a topic that received significant attention in our previous discussion. When it comes to time, we deal with two perspectives: real time, governed by the strict rules of physics, and perceived time, which is how we personally experience the passing of moments. This interplay is influenced by our attention, emotion, and even our age. For example, spending an hour on the beach can feel like a blink of an eye, while that same hour in a boring meeting can seem to drag on forever. This variation isn't due to actual time dilation, it's simply our brain adjusting its internal clock. Speaking about time perception, this brings us to the intriguing world of sacred text.
In many of these, there are passages referring to the idea of time dilation, where a day on Earth might equate to several thousands of years in heaven. It's crucial to stress that these references don't depict the physical time dilation. We are beings bound by the constraints of our sensory experiences. It's entirely possible that there exist realms of reality beyond our own, each with its own unique temporal units. Perhaps in these realms, time as we understand it ceases to hold meaning.
Everything that will happen has already been preordained. The causality, the consequences, all are predetermined.
Within the confines of such a reality, our concept of time on Earth now becomes entirely irrelevant.
Just when you think it sounds too superficial, consider again the concept of a black hole. This is an object so dense that time itself stops. At its core, a black hole might exist outside our conventional understanding of time. A single second could correspond to millions of years outside of it.
All of our equations tell us that an entire new space-time opens up for you. Once you've left the universe you were just in, you will never return to it, but you'll enter another domain.
In the movie, when Cooper was sucked into the black hole, he indeed entered another domain, a psychedelic vortex that was somehow connected to his daughter's bedroom while she was a little kid. And here it is 25 years later in the same bedroom. Between the two timelines, there is still a strong anomalous force at work. It is sent from another space-time dimension by her father. What if I told you that the message her father sent was only a few minutes apart from the other? All of this was made possible through the use of a tesseract. So what exactly is it? And why is the space within it shown in this way? Ultimately, how can this chamber become like a time machine? But the initial question that should be asked here is, how did Cooper get into the tesseract in the first place? From the film, we know that it's because he intends to enlighten the endurance load so that Dr. Brand can reach Edmund's planet. So he flings himself and goes directly into the black hole Gargantua. But you might be asking, how could you enter a black hole and emerge alive at the other end? You may have heard that when someone is pulled into a black hole, their body could be stretched to the size of a spaghetti strand. In addition, if you approach a black hole on a normal perpendicular trajectory, your body will split into 2, then 4, 8, 16, and so on.
However, because the film indicates that this is a spinning black hole, this phenomenon does not occur. And in principle, you should be able to escape the bifurcation of your body by following a specific trajectory. Now, as we are falling towards the black hole, time for us is going to flow more slowly than the rest of the universe. And once Cooper is inside, time is going to stop flowing for him, according to an outside observer.
But Interstellar doesn't stop at Einstein's relativity. To explain what happened next, the movie draws on an even deeper layer of modern physics: Newtonian, relativistic, quantum, and quantum gravity. In our current understanding of quantum gravity, our universe is a membrane, or as physicists would like to call it, a brain. This is the place where you, I, and everything else that exists or has existed lay.
This brain resides in hyperspace, which is a higher dimensional space. And at this point in time, this notion falls within the educated guesses. This is what a warped brain would look like if viewed from hyperspace. In reality, black holes are formed of warped space and warped time, which are made of components from the same brain that we're familiar with.
As a result, the idea that this singularity leads to a portal, which would then enable access to hyperspace, is purely speculative. But we're not done yet. Let's pretend that it may happen for the sake of the movie.
Through this black hole, Cooper escapes our universe brain and uses it as a bridge into hyperspace, essentially allowing him to enter the tesseract, a region of space-time that extends from the singularity of the black hole into hyperspace.
This next segment will be a bit detailed as we explain how the science consultant for the movie intended to showcase it. So just keep that in mind.
First of all, the back face of the tesseract corresponds with Murphy's bedroom. So everything in her bedroom, including herself, is somehow inside the tesseract's back face. And one particular moment in time could be observed in 6 different viewing angles. It might come from above, while also on the right side simultaneously. The second thing, we see that the bedroom has extrusions all around the tesseract, with 2 directions transfers to Cooper's chamber.
Let's look at a specific example to understand this better. Cross-sections through the room that are vertical here travel upward with the passage of time. With the same notion, the cross-sections that are horizontal travel rightward as time passes. Essentially, this cross-section depicts a different viewing angle of Murph's bedroom. Where the 2 extrusions intersect, there is a moment in the bedroom that you could observe its current present, an actual moment of time. This is where the movie defines it as, while extrusions are extending, time is flowing along them.
Cooper has the ability to travel faster than the flow of time in the extrusions, allowing him to explore the tesseract complex. In summary, this weird psychedelic vortex was merely our normal space-time, but with one temporal dimension or time manifested as an accessible spatial dimension.
In this chamber, Cooper could simply go forward and backward in time, as simple as moving diagonally up and down through the tesseract complex.
You've seen that time is represented here as a physical dimension.
It is noted from the movie that the physical objects and fields having 3 spatial dimensions, such as humans, light, and information, cannot move backward in time from one point in our brain to another.
Just like the information about Murph in the past can go to Cooper in the tesseract in the future, but it cannot travel back in time from Cooper to younger Murph. This is due to the fact that the actual warping of space-time prevents it. Cooper, in particular, will never be able to return back in time and alter anything. However, as we see in the movie, gravitational forces may carry messages into the past. The signals can travel back in time from Cooper to Murph, overcoming the one-way barrier.
That's why since the beginning, this movie talks about gravity anomalies. Professor Brandt was only able to partially solve this formulation, with half of the answer being located within the black hole.
The equation couldn't reconcile relativity with quantum mechanics. You need more.
If this equation holds true in real life, I'm guessing this is some sort of a boundary layer problem. Remember how in university level math, you had to solve a partial differential equations that required a few boundary layers for the solutions to be established.
Cooper sends quantum data from the black hole to Murph, indicating that the solution has been found.
It's becoming clearer now.
Cooper's existence in the Tesseract appears to serve a purpose, or to put it another way, his mission is predetermined. We can say this because as soon as the quantum data is securely in Murphy's hand, Cooper's mission is finished. The Tesseract that has been transporting him across hyperspace begins to close.
Also, looking from another point of view, why is it that the Tesseract only features Murphy's bedroom? Out of all the places in the universe, why doesn't it have to be that specific bedroom? Isn't it obvious that she's been predestined to solve the equation? This is the point at which this movie is supposed to hit you.
Cooper across the Tesseract sends that NASA's coordinate to younger Murph. They then proceed to the location, where Cooper is briefed about the secret mission. He leaves Earth and travels to a wormhole. Regrettably, he falls into a black hole and finds himself in the Tesseract. Finally, he sends the quantum data to older Murph. The entire chain of events is one big predetermined loop. The timeline is there since the beginning.
If you think about it, what makes Murph return to the bedroom? Her gut feeling tells her that going back to the childhood room is going to help her solve the gravity equation. But was it all fate?
This, of course, begs the notion of free will in her action. Was it really her who made the split-second decision? Or was it all part of an inextricable chain of events in which whatever happens must always happen, precisely as it is depicted? So you're mistaken if you assume you could modify something in a timeline that has already been laid out. I believe the Novikov's self-consistency principle underpins the concept of time travel in Interstellar. It says that there's just one self-consistent chronology, with no branching of timelines and no capacity to alter the past. In the end, we discovered that there's no definite start point for the loop. It has been continuing ever since creation, and will continue to do so till their universe comes to an end. Every time Cooper appears in the Tesseract, he performs the same thing, by encoding the information in the watch and assisting Murph in solving the equation.
But it still leaves us wondering what would happen if Cooper had decided not to share the quantum data with his daughter. What if I could provide a more realistic scenario of what might actually occur in that case? So in the next topic of this video, we're going to delve into the mind-bending realm of wormholes and parallel universes in Interstellar. A very important disclaimer before we start this topic. It is unknown to scientists whether there is such a thing as parallel universe.
Even the concept of wormholes, which some would argue would be the hypothetical portal to enter an alternate universe, it's also not known to exist. The chances that they exist naturally are exceedingly small.
So what we could say is that they're only a theoretical consequence of the laws of physics, as is known today. But it doesn't stop us from unraveling some of the deepest questions about the cosmos in our reality.
We could describe the physicists' interpretation about these concepts, and I could tell you what physicists think they know about wormholes, time travel, and parallel universes. In 1998, physicist Igor Novikov stated an astonishing idea about wormholes. If their existence are allowed by the laws of physics, Einstein's relativistic law would permit transforming them into some sort of time machine.
But how would that work? Let's explore that statement in detail.
Suppose we have this wormhole system with two different portals. To demonstrate the feasibility of using this wormhole as a time machine, we need the two portals to be carefully positioned at specific locations in the universe. They're arranged such that the time difference between the two places could grow significantly over time. Let's say one stable portal is located somewhere on Earth with person A, while the other end of the wormhole is in orbit around a black hole, and we send person B in there. We can assume both person A and B are the same age while this is happening. So as soon as the wormhole setup is done, we synchronize time between the two portals. Because of the immense gravitational pull near the black hole, time dilation is starting to take effect. For this reason, time for the astronaut at the other end of the wormhole slows down, as seen in the external universe. But time on Earth doesn't slow down, because that is our reference. But seen through the wormhole, the clocks from the two portals run at the same rate. They're still synchronized.
Now suppose for our imagination, we unite the two ends of the wormhole again. Of course, because of the immense time dilation between the two spots, we could see that person B is still young, while person A is very old. That is of course as seen from the external universe. But here's the shocking thing. When you look inside the two openings of the wormhole, both person A and B are the same age. And there you'll see that the two clocks are still synchronized, just like the first time when they were set. Something crazy is going on. It's the fact that you would create a time machine. If person B steps inside the wormhole, he will be able to go back in time, to the time when he's still the same age as person A. Okay, in this very peculiar scenario, there are a couple of things that we could ask ourselves, like, would it be possible for person B to time travel back to the past, immediately at the time when both clocks were synchronized? Would person B then meet his other selves at that moment? Do we need an alternate timeline to explain this paradox?
Theoretical physicist Joseph Polkinski thought about this situation, which now becomes Polkinski's paradox. It's basically the billiard ball version of this scenario, meaning instead of person B, we have a billiard ball that is sent through one portal of the wormhole. Although the idea of a wormhole and a time machine is obviously very speculative, mathematical models have demonstrated that it is possible for a wormhole of some kind to connect different portions of space. That's of course if it's kept open by some form of negative energy.
If this is the case, then the arguments in favor of parallel universes are on our side.
Because given an infinite universe and infinite time, everything is bound to happen somewhere, at another point in space or time.
Now that we have explored this concept from a physics point of view, let's observe how it plays out in the movie Interstellar.
First, we have the origin timeline, what I would call Timeline A. It's simply a timeline where the time travel Cooper exists. So in this timeline, we see the upbringing of Cooper as a space pilot, and then he's engaged in some kind of space mission. It could be that it's the same mission as we see in the movie, or perhaps a totally different one, because we know that Cooper is a former trained NASA pilot, right? My point being, he's on a space mission. And one thing to emphasize here is that he passes the wormhole and then the black hole. He escapes all those magically, which would then leave him inside the Tesseract. Cooper not only transcends the physical constructs of time, he was also in two places at once. You remember the detailed explanation we went through in the last chapter? You can absolutely review that information again if you need to.
So now inside the Tesseract, he consciously decides to transmit the secret NASA's coordinate to his daughter Murph, to a moment before the space mission even began. But the question is, why? And for what reason?
Well, this is basically to allow Cooper to embark on that space mission in the first place. There must be some kind of trigger in that series of events, because without the coordinates, Cooper wouldn't have been able to locate NASA's location, which would imply that he wouldn't be the astronaut that we see in the movie.
Anyway, as you see in a variety of science fiction films, the very act of sending information back in time, or even forcing a different decision in the past, will dramatically alter the course of events. It appears that this new timeline will deviate from the so-called origin timeline. As a result of this, it produces a whole different chronology that I refer to as Timeline B, a parallel timeline.
It is a different parallel possibility that would not otherwise exist if there is no information going backwards in time. And then, because of these coordinates, the movie tells us that Cooper and Murph go to NASA's secret base. He's then introduced to the mission.
Eventually, he goes to space, and Murphy cries, but she becomes a physicist anyway. But hold on, there's still one more significant event here.
Recall that previously inside the Tesseract, not only that Cooper sends the coordinates, he also sends the quantum data to Murph.
As some of you may have guessed, that's actually Cooper from the origin timeline, or Timeline A. This would allow Murphy to solve the gravity equation, thanks to Cooper A's assistance. But at this point, you might be wondering what happens to Cooper B in this chronology. My strong view is that in this timeline B, Cooper dies while descending into the black hole. Here's one of the compelling arguments why I could say that. When Cooper enters the black hole, he is panicking and his heavy breathing is interrupted by a few gasps. He is passing away. But do you know what happens next? We cut to the shot of his son back on Earth. Keep in mind that Dr. Mann says this line somewhere in the movie.
The last thing you're gonna see before you die. The children.
I've got one more proof that I'll show you later. So stick around and let's unravel the rest of the timeline. Although Cooper B is dead, can you recall what happens to Cooper A inside the Tesseract? I mean, after he sends the coordinate to young Murph and the quantum data to adult Murph. Well, you guessed it. The Tesseract collapses and Cooper is suddenly transported to some kind of in-between reality. He makes contact with the spaceship and Dr. Brandt. In our timeline, this is how it looks. This path represents the idea of traveling between two different realities.
Cooper A goes to timeline B, the timeline where basically is not his origin timeline, which brings us to my second proof. When Cooper A appears in this new timeline and reunites with Grandma Murph, I feel that there's definitely something very strange in this particular scene.
What would that be if you had to guess? Well, this is what I'm talking about.
Because my dad promised me.
I find it incredibly weird when one of the characters in the movie speaks in the third person, when she has the clear opportunity to refer to him directly. She had the option to say, "Because you promised me." Grandma Murph may be subconsciously sensing that the Cooper in front of her is not the father from her own timeline. Instead, it's Joseph Cooper from another reality.
There are a few perplexing elements when you analyze the timeline of Interstellar in detail. One of them is this account of higher dimensional beings. Who are they? What would their chronology look like?
The notion that they are the descendants of human from the future is explicitly stated in the movie. They have advanced as a race to such an extent that they could exist in 5 dimensions. For them, time is a physical dimension that can be accessed. From our perspective, as a fellow humans who are held captive by the present, their control over time is intangible.
However, it still leaves open the question of how they came to be. Does the fact that Cooper is the only one who created this alternate timeline have anything to do with it? Here's my speculation.
At the end of the movie, Cooper is seen to reprogram TARS, take control of an advanced ranger, and embark on a new space mission. He takes off for one last time, to reunite with Amelia Brand on Edmund's planet. From this point forward, it's very likely that they will be the parents of the new era of mankind. It could be a millennium before that happens. But once it does, time will no longer be an issue. Because if they become fifth-dimensional beings, they could access the time dimension to their liking.
At this point, I'd like to refer back to the question of who put the wormhole and the Tesseract. Isn't that the higher dimensional beings as referred to in the movie? Perhaps what Professor Brandt says here makes a lot of sense in this case.
Something sent you here. They chose you.
This is an aspect of reality that we don't yet understand, a paradox.
Because Cooper's action to deviate from the origin timeline would eventually confine him inside a loop that is going on for time immemorial. Without him, there won't be any higher dimensional beings, the very same entities that would then build the wormhole and the Tesseract just for him.
I'd like to end this video with a little trivia so you don't feel confused. Let's take a look at this whole chronology once again. Now the puzzle is, what would happen if, for some reason, Cooper doesn't go to the Tesseract? What's going to change in this timeline? You should find the solution to this question to be rather simple.